Hey guys, wanted to talk a little bit about a couple extra topics in chemistry here. Just a couple little things, all right? First up, you've got this idea of solutions. A solution is anytime you mix a couple things together. Just kind of as an example, you could take some hot chocolate powder and mix it into water, and then you'd have hot chocolate, right? The water would be called the solvent, and the hot chocolate powder would be called the solute. And when you mix the solvent and the solute, you get a solution. Okay, so sometimes things are not chemically bound together like molecules; they're just kind of mixed together like solutions. A couple terms here: solubility measures how much solute you can mix into a given amount of solvent. You've probably taken a glass of water, if not, you're welcome to try, and started putting spoonfuls of water in, stirring, putting another spoonful. At some point, you can't get more sugar to mix into the water. It starts to fall out, and you can see it at the bottom of your glass or something. Same thing with salt or whatever. So the solubility there would tell me how much I could mix in there. The concentration is a way to measure how much solute, how much powder I have in the solution, how much hot chocolate there is in the water, or whatever this is. This can also apply to gases and waters, but usually we're thinking about mixing something into a solvent. Water is a common solvent, but some things like oil-based materials would require a different solvent, right? And you know that from cleaning up things, some messes you can clean up with water really well, and some you need to go get some paint thinner or something, and something a little stronger solvent. Same idea here. We want to mix that to dissolve one substance into another. So the concentration tells us how much solute we have per how much solution we have. Last one here is saturated. When you have put all of the hot chocolate powder into the water that you can and can't get any more, then that's called saturated. That's the maximum that you can get in there. Although there is a thing called super saturated. I kind of grayed this out here and did some metallics, but really all you're doing is you're heating up the water so that you can put some more in there. When you heat it, the water expands, makes a little bit extra room between the water molecules and the hot chocolate powder. You can get a little bit more in there. Sometimes people grow crystals. That's kind of an interesting thing to do on your countertop. If you take some water and get it hot and put a whole bunch of sugar or salt in there, and then hang a string in it and let it kind of cool for a way. You may want to get the string wet and roll it in some sugar crystals just to give it a seed so that they have something to start that crystal structure. But you can build some nice looking crystals on your string there. It'll just, those molecules will grab on and form up in a lattice and make some nice crystals. If you choose sugar, then you've got one of those little candy stick things that you see people sell, and you could just eat the rock candy there. If you got salt, I guess you could eat the rock salt, but I don't recommend it. Super saturated, means you've got more in there than it really can have, and it's going to start making crystals as soon as it gets a chance to. Might take a couple days, couple weeks to get it to where you want it to, but as the temperature falls, as that lattice structure does its work, then you're going to have some nice crystals if you want to try that. So enough about solutions. Right here you see a water molecule. We've talked about that. You know that it's a covalent bond between an oxygen atom and two hydrogen atoms. There's a little bit more detail about how that works right here. You've got the hydrogen atom here and here, oxygen atom there. You know that hydrogen has one atom in its outer shell, its only shell, and it would like to have two. So it makes a covalent bond with oxygen here, and you can see that it's kind of counting both of those now. So it's got its two, it's happy. Oxygen just picked up that extra electron from hydrogen. Remember, they're sharing it. They both are counting that towards their grand total. So hydrogen now has two. Over here I've got a second hydrogen. He shares a pair. So hydrogen sees these two in his orbit and says, I'm happy. Oxygen had 6 in the outer shell, would like 8. He got 1 from this guy, one from this guy. So now he's got 8. Everybody's happy. That's the covalent bond that we're used to thinking about. A single shared pair here, single pair, single bond there, and that's the way this works. Now, these extra electrons here that are sharing kind of pulls those together, and maybe a better way to say it would be all these electrons on this side don't like each other, so they kind of spread out as much as possible, right? They're repelled by each other. So I've got more negative charge here than I do on the other side of the molecule. Same thing here. These 2 electrons are shared. They're kind of playing in the middle between these 2 nuclei, and so that leaves the nucleus sticking out the back here. Those hydrogen nuclei are positively charged. The end result here is that I end up with a positive charge on this end of the molecule and a negative charge on this end of the molecule. That's what we call a polar molecule. It's got a polar nature where one end is positive and the other end is negative. That's interesting because polar molecules will kind of group together. It's not a chemical bond, it's just a charge attraction. I've got this positive end right here with the 2 hydrogens. Here's the negative end with that oxygen atom and all those extra electrons kind of smushed in there, and those are attracted. So they make these chains that polar molecules do. Meanwhile, if it's a non-polar molecule, right here, for example, is ethane with 2 carbons and 6 hydrogens. We talked about that last time too. All covalent bonds. These are all covalent bonds, but you can see there's not a positive end and a negative end. It's just like a basketball kind of bouncing around a room, whereas this would be, kind of magnets, and they're going to more or less stick together, right? They're attracted to each other. This is the reason that polar molecules and nonpolar don't mix. I can't mix oil and water. I can stir it up, but it's going to separate right back out. So if you took a glass and put water in it and then poured some oil and stirred it up, you could kind of see the little lumps right there, but those lumps of oil, the drops of oil, but those would start to collect together. The water is heavier, so it's going to fall to the bottom, and the oil is lighter. It's going to float up, and pretty soon you'll be able to see that layer of oil floating on top of the water. This glass actually has a layer of oil on the bottom. It's a thicker, denser oil. Then you got water here and a light oil like cooking oil or something on top. So the densities still work the same way. If it's denser, it's going to sink. If it's lighter, it's going to float. But they're not going to mix because one is polar and they all bond together, not bond, pull together, and the others are non-polar, and the polar molecules kind of push the non-polars out of the way. That's interesting. Here's something else that water can do that's pretty neat. Once in a while, you'll get this water molecule, and this hydrogen nucleus will kind of get bored and wander off. That's called dissociation. Maybe some energy comes in and hits it just right and springs it loose. Maybe it just wants to go for a walk. I don't know, go get some cigarettes or something. I don't know. But you end up with this thing right here with a loose hydrogen nucleus. Remember, that's just a proton. So you got this proton, positive proton floating around, and now you have a hydrogen atom and oxygen atom. That would have 1 proton. This would have 8 protons, so 9. But now I've got 10 electrons. So this thing is an ion, and that's an ion. Here's a positive ion. There's a negative ion. Dissociation. It's separated from what it was supposed to be doing. This dissociation is interesting because that hydrogen, that free hydrogen nucleus there, that proton can come and be attracted to another water molecule, not a bond, but a charge attraction. This guy's positive. He sees that polar negative end there of another water molecule and says, hey, can I come play? And they go, okay, sure. And so then he's hanging on with that guy. That makes what we're calling a hydronium ion. This water molecule was neutral. It just picked up a positive charge. So now this is a positively charged thing that we call a hydronium ion. Meanwhile, the guy that was left behind without that extra hydrogen nucleus, lost a proton there, would be a negatively charged hydroxide ion. Well, this is what makes acids and bases. If you've got a whole bunch of hydronium ions, then you're looking at an acid. So hydrochloric acid and lemon juice and all sorts of things are acid or acidic. And it's because they've got more of these things. Meanwhile, bases like soap, like Clorox, like some other stuff, those would all have they would have more hydroxide ions than hydronium ions. There's a way that you measure and calculate how much of each there is, but we don't need to go into that. I just want you to know that this is the thing that happens to make acids and bases. Here's a little bit of information about acids and bases. We've already said that acids have more hydronium ions. They have a positive electric charge because it's just, they picked up a proton. Acids taste sour. You can remember that with lemon juice right there. Litmus paper turns pink or pinkish red in an acid solution. So right here you see a piece of litmus paper. It's a piece of paper that's been soaked in chemical, but that the color of the paper will change when it's exposed to an acid or a base. Right here you can see that it's turned pink, and that says looking at an acid here, and lemons are acidic. Meanwhile, bases have more hydroxides. They have a negative electric charge. Bases taste bitter and feel slippery. Easiest thing to do is to remember that we're talking about soap. Soap is a base, right? And it's going to feel slippery, and your mama might have showed you that it tastes bitter when you're a child. I don't know. But litmus paper is going to turn blue. So there's a little bit of litmus paper. You can see the scale right there. I'm going to tell you about the scale in just a second. But things can be more acidic or less acidic or more basic, and go through like that. I did put the little sticker on here for corrosive, the little warning sign. You got to love the little warning signs they make up. Acids and bases are both corrosive because there is either that extra proton or a missing proton. They're chemically reactive, and they cause matter to break down and cause chemical reactions. So watch out for acids and bases. Here's the scale that we use. It's called the pH scale. I believe that stands for percent hydrogen or percent hydronium, something like that. It's a logarithmic scale. You don't need to know about the mathematics of it or anything, but it runs from acid at the low numbers 1, 2, 3, all the way up to a base being 14 up here. So neutral is right smack in the middle. If you just take water, that is not acidic, it's not basic, it's just neutral, okay? But as you add more hydronium ions, the more you add, the farther you're going to go this way. So you've got stomach acid is stronger than lemon juice, is stronger than apple juice, is stronger than tomato juice, is stronger than coffee and milk, and then you're back to neutral again. Meanwhile, the bases work off this way. The strongest one would be 14, comes down to 13, 12, 11, 10, all the way down like that. And you can see some common household type things there. You might have seen where people put bleach on their jeans or something, right? And it bleaches it out, and if you leave it on there, it'll actually break down the fibers, the cotton. It'll react with that and break it down. Sometimes people put bleach in their hair, and sometimes they end up with no hair when they do that. I don't have any hair, but it's not because I put bleach in it, all right? Trust me. You got to watch out for these things out on the ends. That's where the strong acids and strong bases are. I put this on here. Organic chemistry is something you hear about, and people are usually all kind of scared about it. It means that it's carbon-based, that I've got carbon atoms in there that are doing interesting things. You remember that carbon had 4 electrons in its outer shell, and as such, it was really easy to make bonds with. It can make bonds with other carbon atoms, and right here you see something that's solely carbon atoms. This is sometimes called Buckminster Fullerene, I think. Buckminster Fuller was an architect and artist and free thinker, interesting guy. But anyway, he started making shapes that look like this, not of carbon, but just sculpture and architecture. He would make all those domes, geodesic domes and stuff, were his work way back in the 30s or 40s, I believe. Um, well, they found that carbon can do that, and it's 60 atoms of carbon all tied together in covalent bonds, and it makes this neat little ball. Here you see a hydrocarbon, right? Carbon, the black carbon atoms in the middle, and the white hydrogens. We've talked about hydrocarbons, so you know something about that. It can make like a little ring there. You see six carbons. Here it's kind of dark gray instead of black. And we just saw a chemical reaction there. It's going to loop again here. Right there, you see the six. That's a benzene ring right there when you get those six carbons in a circle. But see, this green guy came over here and pulled this stuff off, and now it's down to five. So these things can change and do interesting things. Here's kind of a nice flat thing going around. Got a couple other atoms mixed in there too. But so that's organic chemistry, is all about that. The reason we're interested in organic chemistry is because we're based on carbon, right? Animals and plants and all life is carbon based. And if you take it to the extreme, here is DNA, and you can see that it's all organic chemistry. It's all hydrogen, oxygen, nitrogen, carbon, phosphorus. There's a couple other atoms that pop in to make the human body, selenium and silicon and stuff. But in the DNA, which is our code, which is the instruction set for how to make another human, it's just organic chemistry, you know? It's covalent bonds holding atoms together, and these rungs of this spiral ladder right here are the information to make a copy of this DNA and to make a copy of yourself. And so, you know, if you have kids or people that do, they mix the DNA and it makes a new genetic pattern, and those cells begin replicating, and so this is, you know, kind of the essence of life right here. Goes all the way back. Physical science kind of turns it over to biology here, and you know, we in physical science we're not interested in biology and anatomy and all the animals and plants and all that stuff, botany, but you know, this is kind of the separation point. It all comes back to physical science and chemistry and even physics with, you know, it's physics with the charge attractions and the particles that are here and stuff. So it's all tied together. It's all pretty neat. And that's all I got for you today. Today's kind of just some extra topics tossed in, and let me know if I can do anything to help. And thanks for stopping by. Have a great day.